Our next up is we're going to be bringing on Andrew, and Andrew Nasenko is going to be speaking to us about combining asynchrony and coroutines. And I already said it's coroutines, right?
Coroutines.
Coroutines, great.
Yeah.
So, and this is a C#8 feature, correct?
That's a C#8 feature. Yeah.
Okay, great.
We'll cover that.
All right, so I will just bring you on and I will disappear.
Thank you very much. Hi, friends. My name is Andrew Nasenko. I'm a software developer and entrepreneur. My previous role was with Nuance Communications, and I used to work there for many years as a part of tremendous team of talented and wonderful people. I live and work in Australia, Australian of Ukrainian origins, and I'd like to say big thank you for Sydney AltNet, who were the audience for the initial version of this talk. And of course, thank you to my wife and to my son for their patience and for letting me prepare for this event. We'll be talking about asynchronous coroutines with C#. This is the first time I'm giving a talk on a global scale, and I'm a bit nervous, so I apologize if anything goes wrong. So any questions, you can easily find me on TechWeb by my Twitter handle. I'd be happy to follow up. So let's begin. I'd like to start with a very simple C# method for rendering fade effect in Unity game engine. So what's going on here? This sounds familiar. This is a numerator. This sounds also familiar. We all use link in C# to produce data sequentially. But why do we have this null as a result here? And the answer is Unity doesn't use this method for generating data. It uses it to suspend the execution flow of this for loop to be resumed later. So we actually see the fade effect on the screen of the game or whatever it is. What are coroutines? Coroutines are functions that can be suspended, resumed, and executed cooperatively, and often on the same thread. At least that's what Wikipedia says. And this is how they are different from thread routines, which are typically preemptively multitasked. Coroutines is nothing new. They are old and mature concept. I'm myself old enough to remember Windows 3 with its yield method. We used to call it when we needed to organize cooperative multitasking between all those apps. They were executed on a single thread. Luckily, nowadays, coroutines are easy to implement thanks to the modern language support that C# has, which takes excellent care of generating implicit state machine logic for our coroutine methods. What is a state machine? Let's have a quick look. And I'm using this pretty awesome sharplab.io website. On the left-hand side, we have a very basic coroutine, enumerable based. It's all it does, it just iterates with 80 steps and generates a string of a character on the console. At the right-hand side, we see what the compiler generated for us, and it's just a bunch of weird code. What it is actually, it's just like a hidden class with a bunch of delegates, callbacks. All it does is to allow us to suspend and resume the execution flow of this for loop. All right, so back to slides. What are coroutines useful for? Coroutines are useful, can be useful for script-like scenarios where we want to suspend and resume the execution flow of something after each logical step. And the nice thing is we have explicit control over when to resume the execution and when to suspend it. Many long-running background workflows can potentially be structured as coroutines. For example, spell checking pattern, syntax highlighting, static code analysis. One real-life example that I'm going to be cover in this talk is automated UI testing. Hopefully I'll have time for that. Let's do some coding. Let's start with a simple case, coroutines without internal asynchrony. This approach has been in use since yield keyword was introduced in C#, I believe it's version 2, so over a decade by now, and that allows to implement state machines for IEnumerable and IEnumerator methods. Traditionally, we used yield return for synchronous generation of data sequences. With coroutines, we use it as a tool to break the code into multiple individually executed steps. And as I said before, this technique has been popularized by frameworks like Unity Game Engine. There's also Caliburn Micro for WPF and some others. Let's keep it simple. So this, back again to the coroutine A. Again, all it does is generates a run of A characters. In real life, it could be doing something like updating view model, for example, or anything else. But we want to keep things simple here. And just to show what it's about, we have also coroutine B that looks pretty much the same. It outputs a string of B characters, and we want them to run concurrently on the same thread. Let's go to Visual Studio and actually run the code. So I have this little Windows Forms application as a playground, and that'd be the first demo. So you saw the code, now they run in parallel. How do they run? There must be something that executes them, that drives them. Let's go back to the slides. The workflow goes like that. So we have that UI thread here. We have coroutine A that yields to B, B yields to A yields to B, and on and on. And the execution is driven by the code which we called coroutine driver. The purpose of it is to first of all start, suspend, resume, and end coroutines. In our example, it also combines multiple IEnumerables into a single sequence, because we want to interleave A and B. And then it executes that resulting sequence one step at a time by calling IEnumerable move next upon a certain time interval. The coroutine driver code looks like this. Actually, let's go to Visual Studio and have a closer look. So this is here. Yeah, as I said, this is the driver itself is a task-based method because we do something on particular timeline. We create that combined sequence of A and B here, get IEnumerable for it. We start the Windows Forms timer, and upon every single tick, what we do, we call move next on that combined sequence of A and B. And we do that in the loop. We do that until move next returns false, or until the cancellation token is signaled. So in our case, we just loop until I click cancel button. So that's nice and simple. Back to the slides. Why not simply use async await? So instead of using IEnumerable, we could have just created something like that, a simple task-based method that does something like await task yield inside. Why is it not so good? Because we only would be notified about the completion of the whole method, not about individual steps. We can potentially control individual steps, but for that we would have to enroll something like a custom task scheduler or custom synchronization context, or do custom awaitable instead of this task yield. All right. What if we still want to use asynchrony inside methods like coroutine A or coroutine B? It can be useful for many reasons. We want to wait for something like, I don't know, a WebSocket message or mouse move or keyboard button, and then suspend and resume. Ideally, we'd like to use async await for awaiting the result of actual asynchronous API, and use yield return for suspending the execution flow. Well, that wasn't possible until recently, until C# 8.0, which introduced language support for asynchronous iterators. And these are the things, a bunch of new interfaces and language features. They are nothing more than counterparts for already, for the things that we already know, that's IEnumerable, IEnumerator, IDisposable, for each and using, but they are asynchronous, they don't block the thread, and they allow us to work with asynchronous APIs. Let's reproduce what we've done so far with IEnumerable based coroutines, but using IAsyncEnumerable this time. So we still want to have certain minimum time interval between yield return continuations, but to add some real asynchrony, we want to proceed to the next step when the UI thread is idle. Just something useful. We don't want to, we have background workflow, we don't want to spam the UI thread with work. And we also want to do that if there is no pending input on the UI thread message queue. So for that, I created a little helper class, which is called input idler. You can find it in my GitHub repo for this talk. And I'm going to use it inside coroutine A and coroutine B. So coroutine A now is IAsyncEnumerable based. There we have our little asynchrony here. We await the result of this input idler. And just as before, we just return the current for index as a progress notification. At coroutine B, we may want to change a bit to make it different. We want to slow it down because now we can. So we also add that task delay. Supposedly it will run slower than coroutine A. Let's do some demo. Same application, now the second demo. There we go. So they both run concurrently, still on the same UI thread. B is a bit slower. Now let's do that dirty trick to start working on the UI thread. This is not something that we all should be doing, but just because we can for this demo, that's what it does. It just does dirty work on the UI thread, and you can see both of them are on hold while the UI thread is busy. All right, so that's nice. Back to the slides. Yeah, it's actually also interesting to have a look at that coroutine driver. I believe it's got even simpler than for non-asynchronous version. So we have that drive coroutine async method that accepts a bunch of coroutines as IAsyncEnumerable, and then we start them all concurrently, and then we iterate through each of them using a wait for each loop, and that's our delay here, which is like now it's a minimum delay because we have no control over what's going inside coroutine. It may stop forever, so we at least provision for some minimum time interval. Now let's divert a bit and demystify what is a wait for each loop. Back to Visual Studio. It's very basic. It's very simple when you get down to it. So all it does, the for each loop accepts an IEnumerable cancellation token, and we obtain IAsyncEnumerator on that IAsyncEnumerable. So basically, IAsyncEnumerable is a factory for IAsyncEnumerator. And then we plainly loop through the next move next async. Synchronously, we await the result of move next async. If it's false, we stop. Otherwise, we just do something with the data that we received. So and also we can that can be synchronous, something that we do with it, or it can be asynchronous like that. Hope it makes sense. Back to the slides. Now the fun part. What if you want to synchronize coroutine A and coroutine B? Like A depends on something that is going inside B. We may say that coroutine A and B serve as producers to the coroutine driver, which is the consumer part of it. But both A and B run independently. They are not even aware of each other's existence. What if you want to make them aware of each other? We can't just pass IEnumerable for B into IEnumerable for A into B and vice versa. We can't do that. So we need some kind of buffer. And I come up with a special helper class for that, which is called Async Coroutine Proxy. It wraps a very awesome .NET channel class, which we'll talk about a bit later, as a synchronous buffer for buffering progress notifications of each coroutine. Let's have a look at the code again. It's going to be this demo. So what we want to do still two console-based coroutines, but we want coroutine A to be on hold while B is progressing here. Then B is on hold, A is progressing, and then they both continue together. They kind of know about each other now, and they synchronize their workflow upon each other. And again, we can just do our dirty work on the UI thread, and they both on hold. And then when the work's done, they both continue. Let's look at the code. Oops, that happens. Yeah, before we look at the code, I want to touch a bit that channel class that I mentioned previously. So channel is like a pipe. We can push objects into one side of the pipe with channel writer, and then we fetch them as a synchronous stream from the other side of the pipe with channel reader. And so it looks like that. We have coroutine A, we have proxy for A, and we have coroutine B, and we have proxy for B. And the progress of A goes into proxy A, the progress of B goes into proxy B, and every time A wants to synchronize upon B, it speaks to that proxy of B. And the same thing is when B wants to synchronize upon A, it speaks to the proxy of A, not directly. Because if we did it directly, we could have ended up as some sort of naughty asynchronous deadlock, which is fun to experiment if you have time with. Let's look at the code. So that'd be this one. And let's look at the code of coroutine A. So that's it.
Andrew, can you zoom in the code a little bit? I had a few people saying they're having trouble reading it.
Sure.
That's a lot better. Thank you.
Is that better? Sorry about that. So, all right. So that's coroutine A. It accepts that proxy, and the proxy is itself. We make it async enumerable. Then for the first part, when the coroutine A is on hold, it just draws that little throwbar, like spinning wheel. It iterates asynchronously through B, and when the B is at step 4, it breaks out of this loop and it starts its own workflows. It starts its own 80 steps, and we have a delay here, and it basically produces, as a result, the current iteration. Let's look at B. It's a bit different, but also pretty basic. So we have that for loop for 80 steps, and first of all, we just do our first 40 steps. When we add step 40, we pause. We now start looking for coroutine A. And when coroutine A is step 40, we also break out of this and we continue our outer loop until we finish. And what's nice about this is instead of using a wait for each, we can actually use a synchronous link. And it's very powerful. I consume that system link async package, and now hopefully it will work. What I'm going to do is I'm going to do proxy A, take 40, take 40, excuse me, take 40, then I'm gonna use last or default. I think that should do, and of course I need to await this. So there's not gonna be the throwbar now, but let's have a quick run. Yeah, there we go, it stopped. No throwbar, but it stopped, and now it continues. So yeah, we can use asynchronous link, and it's very powerful. I only created the service myself, but I think it's pretty cool. So how much time we still have? Okay, back to the slides. Oh yeah, let's touch the base on what is that proxy code that uses the channel. The proxy code is actually pretty simple itself as well. All it does is it creates an unbound channel. An unbound channel is only limited by the amount of memory you have. You can push as much as you have memory available. And it exposes the reader end of that channel as another async enumerable. So that's what coroutine B takes in when it needs to speak to coroutine A. And then basically it just uses another await for each loop to iterate through coroutine which it is proxying to, and writes the progress notifications to the writer end of the channel, and that it completes the channel when that sequence is complete or is cancelled through the token. So yes, it's pretty simple as well. Now about real-world example. So I actually learned all that stuff when I started learning asynchronous strings in C#, and I wanted to apply it to something. And I have that side project that is a sort of copy-paste productivity improvement tool. I hate when I paste formatted text. I think everyone does. So we have Control-Shift-C that usually works, but sometimes it doesn't. Or sometimes you want to paste something into terminal window and it just get executed. So I wanted a little app to help me with my bad habits. And all it does, it just uses Windows Send Input API to simulate user input. It strips out the formatting from the clipboard and just spits it out character by character to the currently active app. And I needed I need a test for that, to automated test. So that's what I come up with. So I have a foreground thread that has a Windows form containing just a text box. And then I have a background thread that calls send input. Maybe a decade ago I need to synchronize upon these two workflows, because I need to know when the window is ready to accept the characters, when the characters has been processed and sent back what actually is inside the text box. So I had to synchronize, and previously I would use something like manual reset event and wait one to block. And the thing is, these two workflows that actually run on UI threads, both of them. The thread that has a message loop, and by blocking it, I would have opened a box of worms. So, but luckily today I can use asynchronous coroutines for that. So anytime background coroutine wants to speak to foreground coroutine, I can send the message with this yield return, and anytime it expects something from the foreground coroutine, it does it through await get next. So let's have a look at the code. Let's go to the test explorer. Let's first have a run of it. So that's a foreground window, and the background thread just sends some input and multi-line input, and at the end of it. So it's very basic, but behind the scene there's lots of stuff going on. So I have that foreground coroutine, which is async enumerable, and it has like 4 states. Ready state, text received, cleared the text, and the finish. And when it starts, it basically begins with it does yield return to return the message to the background coroutine that it is ready. And after that, it is suspended because we made the return. The state machine is in suspended state. We'll get to the background later, but the next step, when it is resumed, it now awaits for a message from the background thread to background coroutine to make sure that now the background coroutine is ready. So it awaits for a message, verifies it is ready, and that proceeds to the next step. And the next step, it again awaits for the message to get something that the text was sent, and when the text was sent, it actually reads the text from the text box and submits it back as another message as text received. And so it's pretty much linear workflow. We don't have even any loops here. Let's look at the background coroutine. So background coroutine is very similar. Also runs on its own UI thread. It has ready state, text send, finish state, and it also starts like notifying the foreground that we are ready, and then it expects a message from the foreground that the foreground is ready here, and then it basically simulates the typing by sending that text, and then it notifies that the text has been sent, and then it awaits for another message to confirm that the text has been received. It verifies we received what we sent, and stuff like that. So what I like about that, it's they actually run in parallel, not even concurrently, because they run on different threads, but they synchronize at particular points when they need to, and everything is non-blocking, so there is not a single bit of the blocking code here. I think I just scratched the surface of it. There must be, yeah, that's, if you like to make a picture, it will take you to my GitHub repo for this project. Summing it up, I think that asynchronous coroutines may help with structuring any asynchronous workflows, and including certain consumer-producer scenarios. They are especially handy where there is no clear role separation between producer and consumer. And similar problems, of course, can be solved by more like mature and powerful toolkits like reactive extensions or TPL data flow. But those might have a bit of steep learning curve. And here we just deal with language constructs, the syntax sugar that C# isolates us from. Like all the mechanics that goes behind the scene. And also this concept can be used with some other languages, those which support asynchronous iterators, including modern JavaScript. And that's it. Yeah, I have reference section. You can find all of that in my GitHub repo, and just if you need to get to it, just search for my Twitter handle. It's know the ratio. Thanks for watching that. I'm happy to answer any questions.
Yeah, wow, that was really interesting. We got a lot of people saying they're drooling over it. It looks amazing. We had some other people saying, wow, this is a little confusing and it's a lot to learn. So I think I think we gave you a very short time to speak in, right? So you have to kind of pack it in.
Yeah, I tried to squeeze in a bit. I could go on for more. But
well,
yeah, I mean, it might sound complex, but it's actually simple as you get to it with pretty much everything else, right?
Yeah, and I think it's great that you're providing that sample code that people can look at and test. I had a few questions. One is, are there cases where the overhead of adding in the async and the coroutines and that sort of thing, like, is there much of an overhead in doing that?
As my answer would be simple, as with anyone else, don't do micro optimization until you really need to do profiling. And there are lots of questions on Stack Overflow about that, and some of them I myself answered. It's actually, the overhead is pretty low if you get down to it. It's the convenience. I would pick convenience anytime over the overhead.
Okay, that makes sense. How do you showed some different options, like including link and like several things that you step through. How do you? I mean, the link example looks pretty simple. Just from a lines of code point of view, how do you choose between those different options?
To be honest, I only used asynchronous link in this particular example.
Okay.
So
okay.
yeah, but I imagine there's a bit of learning curve to it as well. But if you think about it, just abstract yourself from asynchrony, and if you are familiar with synchronous link, asynchronous link is not much different. It just we used to do pull in for data with synchronous link. With asynchronous link, it's more like we expect a push. So we people who are familiar with reactive extensions will probably see a lot of common in this. So it's up to you to decide. I prefer language constructs. I prefer a wait for loop. I prefer async disposables. I prefer whatever language can provide me with.
I naturally fall back to that too. I can set a breakpoint on something and I can visualize in my head what's happening.
And that's how it's different from reactive extensions. It's easier to debug because it's actually kind of pseudo-linear. You can put a breakpoint, step through it. I like it.
Yeah. I had one other question, which is, when you're debugging, are there strange cases, or do you have any tips and tricks for debugging things when they're not working how you expect?
I actually I would say there is no like trickery. And that's what I like about it. If you're familiar with synchronous debugging, I think Visual Studio does a lot of good work to give you the same experience for asynchronous debugging. There is a synchronous stack, and you can actually see like what it is like that nesting level of asynchronous calls. So it's pretty nice. I didn't face any issues debugging this one.
Great. Okay. Well, we're just over time, so thanks a lot. Yep. Great. Appreciated your talk. I'll
Thank you
be
very
checking
much,
this
guys.
out later. Okay.
Bye.
Bye.